So I'll wait for your signal to proceed.
Yes, yes. That's right. Yeah, you can start.
Yeah, sure. Yeah, so this is a topic which is it was initially not planned to be a part of the course. Yeah, let me know if I'm not clearly audible at any point in time. My internet connection is kind of shaky, so that might create some problems, but hopefully not too much.
You want to make it
So
full
anyway,
screen?
hello.
Do you want to make it full screen?
Oh no, this is just a PDF. Yeah, so right now this is just a PDF, and
I
it,
understand, but
yeah, so I can increase the.
no, that's okay. Yeah, yeah. So it's yeah. Okay, go on. Yeah. So whichever way, that's fine.
Yeah, now I've lost it, so I'll have to find out where it
Oh,
is.
so there is some lines. Why is the lines?
Yeah, I think there's some lag in. Okay, anyway, yeah. So this is just to say that this is one of the early chapters from the book by Aus. Yeah. So initially we had not planned to talk about verification of RNN, but this is some very recent work, and yeah, and we were thinking that it makes for a good end to the course, because this also leaves some open directions which some of you may want to pursue depending on your interests, of course. Yeah, so this was initially not planned to be a part of the course. In fact, it was last week itself that we decided that it'll be interesting to cover this topic. And yeah, so I apologize, I tried to put some slides together in the last moment, but somehow that did not compile well into a deck, so I'll postpone that to the next one, the next class. And today I'll use the paper itself to try and take you through this work. So this one is about recurrent neural networks which have loops, as you can see in this figure shown here, the figure 2.7 as it is called here. Yeah. So the idea is that, so why do you need recurrent neural networks? So remember that we have these traditional feed forward neural networks, right? So there you have an input which is a fixed size. You know the size of the input, so you cannot really so if you are doing something with, let's say, with English sentences where the sentences can be of varying lengths, then you can't use one of these networks that we have been looking at, these feed forward neural networks. So you need a recurrent neural network in these cases, and there are many applications. In fact, speech recognition and machine translation and so on. So these are some popular applications, and for these you need some dynamic behavior, so that even streaming inputs as they come, or varying length inputs. So in order to support these things, you need what are called recurrent neural networks. Okay, so in principle, this is not very different from feed forward neural network, because you can unroll the whole thing as yeah. See, these lines are disturbing. I don't know why they're okay. Yeah,
Now it's yeah. Now
correct. Yeah, so you can unroll yeah. So I will not scroll up again because the lines may reappear. But the you remember the one that we had seen above, it had a loop in the middle, and the point is that you can unroll this thing into this thing where this figure 2.8, where you have an unrolled recurrent neural network, and this is like a feed forward neural network where you can, which you can treat the way we have been treating these networks. So you can do analysis, you can do verification, and so on. Okay, so therefore, so the issue of loops when it comes to neural networks is not very difficult to handle, because there's always this length which they can be unrolled, and this length it can be determined statically without really executing the network. So this chapter also talks about the same thing, but it's not very difficult to see that it is indeed possible to do so. So you can unroll the network and then treat it as a feed forward neural network. and do your analysis. The only thing is that see, neural network verification, we had seen this when we were looking at reluplex, and I think even before that when we were trying to see if these things can be verified. We had seen that these things can be exponential in terms of the size of the network, and therefore to grow a network by unrolling is perhaps not the best thing to do when you have the task of verification at hand. So therefore, what this paper does, and I'll move to the paper now. This is just for the motivation part. So correct. Yeah. So this paper, so this paper talks about. So I'll show you the title of this paper. So this one says verifying recurrent neural networks using what is called invariant inference. So those of you who don't understand what invariant inference is, or what even invariants are, we can address this problem of in understanding what invariants are and how to infer them later. Let's not worry about this part now. What we'll see today mostly is what does it mean to verify an RNN, and what are the kind of things that one can do. Okay, and of course we'll get to the invariant inference part also later, but let's postpone that for now once again. Yeah. Yeah, let's not worry about the lines. We know one way of getting rid of them now. Yeah. So this is, so let's take an example. Let's begin with an example of a recurrent neural network. So what these recurrent neural networks have, they have what are called memory units. Okay. So here is an example of a very simple network. So if you ignore the box, the square on top, and if you ignore the dotted arrow that goes to the square box, and the solid arrow that comes out of it, if you ignore those box and those two arrows, what you see, what remains is a simple feed forward neural network, where you have input node v1 comma 1, or 11 as I'll call it. So you have an input node of v11, you have a hidden node which is 21, and we'll assume relu as the activation function. So this is a hidden neuron with relu activation function, and the output node is 31. And of course there are edge weights like we had, and we are continuing to ignore biases for now, because as we know, they don't really add to the expressive power. Okay, so this is what is a standard feed forward neural network, and in RNN, what can happen is that these neurons, these hidden neurons, can have a memory unit associated with them, through which they will track what has happened in the past, or which is necessary for handling, let's say, streaming inputs and so on. Okay, so let's try to understand the semantics of this very simple network which is shown here. Okay, so the output has to be understood in terms of time steps. Okay, so there's not one input and one output. There's a streaming set of there's streaming inputs, and therefore there are multiple outputs. Okay, and the whole thing is thought of in terms of time steps. Okay, so this one, so I'm focusing on the table to the left of the figure. uh, yeah, so there are 4 time steps that are being talked about here: time step 1, 2, 3, and 4. Okay, so what happens is, so v1 comma 1 was the input neuron. So there are different inputs at different time steps. So at the time step 1, the input is 0.5, which becomes 1.5 at time step 2, then -1 at time step 3, and then -3 at time step 4. Okay, so of course, as the input changes, the value at these other neurons also change. Okay, so since the edge between 11 and 21 has the weight 1, so the input gets propagated directly to 21, except that if it is negative, then ReLU has to be applied on that. Okay. Okay, so what happens in the first time instance? Okay, so when you begin, okay, so these are the standard neurons, and these square boxes are what are called memory units. Okay, so you have nothing. So when you begin execution at time step 1, you have nothing in the memory unit, so that which is denoted as 0. Okay, so therefore the 21 tilde is 0 in the beginning at time step 1, as you can see in the table. Okay, so then how does it work? So you get half as input, which gets propagated to 21. So you get half at 21, and then that half is put back into the memory unit, which was 0 now. So it is put into the memory unit, which will appear only in the next time step. So right now it is 0, and since 0 was available at the memory unit, so the incoming arrow from the memory unit is treated as, so memory unit is treated as a standard neuron. Okay, so at 21, how do you calculate the value? You calculate the value at 11, v11 into 1 plus v21 tilde into 1, and ReLU applied on this sum of products. Okay. Okay, so you have 0 into 1 coming from 21 tilde, you have half into 1 coming from 11. So therefore at 21 the value is half plus 0, which is half. ReLU applied on half is half, so therefore half is what is propagated to 31, and therefore you can see that at time step 1 the value at 31 is half. Okay, so this is how it happens, except that now that half was calculated at 21, that half is stored into the memory unit 21 tilde, so that it is available at the next time step. So at time step 2, the input has changed, it has become half. Okay, so now what is the value at 21? The value at 21 is half times 1, which is coming from 11, plus sorry, 1.5 times 1, which is coming from 11, plus half times 1, which is coming from 21 tilde. Okay, so this 1.5 and half gives you 2. So therefore the value at 21 is 2, and 2 is what is propagated to 31. Okay, and then this 2 gets written into the memory unit. Okay, so therefore what happens at time step 3? The input is -1, so -1 gets propagated from this side. From the 21 tilde, 2 comes 2 times 1 comes to this 21 neuron, and therefore the sum is 2 minus 1, which is 1. 1 is bigger than 0, so therefore ReLU applied on 1 is 1, and therefore 1 is what gets propagated here to 31. Okay, so this was at time step 3. Okay, then at time step 4, when the input is -3, so -3 gets propagated from 11, and 1 comes from 21 tilde. So -3 plus 1 is -2. Since -2 is less than 0, ReLU will reset it to 0, and therefore 0 is what gets propagated at 31. Okay, so this is how recurrent neural networks behave. So they have a memory unit which store what had happened in the previous time step, so that it's available for computation at the next time step, and that's the general idea. Okay, so this is how they behave, and of course you have as many memory units as these neurons. Okay, yeah, so I'm assuming that it is clear, and I'll go ahead. Of course, you can interrupt me if you have any questions at any point. Okay, so this is what you have as a recurrent neural networks, and this is how they behave. Okay, now of course, if you have to verify certain properties for these networks, as we saw just now, you can unroll them into a bigger network, and that is what was being done until this paper. Okay, and this is a very recent paper. In fact, this paper appeared, I think, in sometime in October 2020, which is, yeah, it was, yeah, I think this ATWA, this is from a conference called ATWA, and I think it usually happens in October every year. So this is last month's paper. Okay, and these guys say that until yeah, I mean, any other neural net, any other RNN verification technique that they know of uses unrolling to unroll it into a bigger network, and then do the verification, which is certainly not good, because it increases the size of the network, and verification is exponential in the network size. Okay. So this is the idea. So now we have one such network, right? So this one, and we understand how it behaves. Okay. So let's try to now get to some properties of this network, and we'll see what these properties mean, and how we can prove those properties. Okay. Yeah, I'll very quickly go back and check if I have missed anything. Unlikely, but I'll check it anyway. Yeah, I'm sorry for this back and forth. I tried to put some slides together. Somehow, for lack of time, I could not. Yeah, I could not get it done. And yeah, so anyway, so this is the idea. Okay. Okay, so I'll go through, this one paragraph from the intro, and I'll try to tell you what this paper might be, what this paper is aimed at. Okay, so these guys suggest a new approach for RNN verification, which of course, the whole motivation is to achieve a greater scalability than what you can get by unrolling. Okay. And the way that they will do this is by reducing the RNN verification problem into what is called, what they call an FFNN verification problem, which is nothing but FFNN is nothing but feed forward neural networks, which is the kind of things that we have been looking at. Okay, so they will reduce the RNN verification problem into the feed forward verification problem. And once you have reduced the problem into feed forward verification, we know enough techniques to do it. One is that you can employ Z3 directly if it scales. If it does not scale, then there is also this reluplex technique, which can handle relu nodes in a nice way, so that you don't have to always split on the relu nodes. Okay. So this is the idea. The idea is to reduce this RNN verification problem into a feed forward neural network verification problem. Okay. But the idea is that, this reduction will happen independent of the number of inputs. So basically, this reduction will happen by keeping the size of the RNN, keeping the size of the feed forward network the same as that of RNN, plus or minus a few nodes, but it will not be unrolled and increased by a multiple. Okay, some additional neurons may be added, but roughly the size will be the same. Okay. Okay, so how will this be done? So this will be done in two steps. So in the first step, this paper creates, given an RNN, the idea is to create a feed forward network that over approximates the RNN, but at least the size is the same. So it's an over approximation of the same size. Okay. And then, of course, the second step is to verify the property on this over approximate network. Okay, so whenever you're verifying property, whenever you're over approximating and trying to verify a property, you can always go wrong. Okay, in the sense that, you may have over approximated too much, and therefore, you may not be able to prove that the property holds, even if it holds. Okay. So this is a problem, and then that can be dealt with in some ways, but we will get to those ways later. The idea is to over approximate an RNN into an FFNN of the same size, and then to verify the feed forward network using existing techniques. By existing techniques, we actually mean, reluplex and such things. Okay, so this is the idea. Correct. Okay. So yeah. So now, some of you may be able to recollect that we had this. Remember, we had this feed forward verification problem, right? And this problem was nothing but a three tuple. What were the three tuples? There was this precondition, which is some constraint on the inputs typically, and then there was this network, and then there was a post condition, which is the property or the negation of the property, right? So you had this three tuple, the precondition, the network, and the post condition. And this is how a verification query look like. In here in RNN, there is a fourth component, which is the time component. Okay. So there is this component Tmax. So Tmax is a number which is a bound on the time interval for which the property should hold. Okay. So your properties are such that they hold for some time, and we will look at a concrete example immediately. Okay. Okay. And other than this time factor, what P and Q include is linear constraints over the network's input and output. And I will get back to a concrete example. Okay, so we have seen this network that we looked at in detail for 4 time steps. This one. Okay, so this is something that we have looked at. Okay, so now, yeah. So as a running example, see, these guys are they have defined a property for this thing, and which is what we are going to be looking at. Okay, so you need 4 things, right? So you need a precondition, you need a network, you need a post condition, and you need what is called this Tmax. Okay, so the network we have already, right? The one that we had seen. Okay, so let's look at some preconditions. So here there's a precondition of this form. What does this precondition say? This precondition says that look, the input at the tth time will lie between -3 and 3. Okay, this is what this constraint says. Okay, so the input at the tth time step will lie between -3 and 3. But then this property, there's a conjunct over t from 1 to 5. So basically this says that, at all 5 time steps, the input will lie between -3 and 3. Okay, which is to say that, so T max here is 5, that we are going to be talking only about 5 time steps. The precondition says that the input will always be between -3 and 3. Okay, this is what is the precondition on the input. Okay, what is the output predicate? The output predicate says that the output, which was 31, should be greater than or equal to 16 for some t. Notice that there's a disjunct here. So for at least one of the t's between 1 to 5, the output at the tth time step should be greater than or equal to 16. Okay, so this is the post condition. So we have a precondition, we have a post condition, we have a T max, which is the interval, the bound on the time for which we are going to verify this property, which is 5, and we have the network, which was specified earlier, right, on the last page in the figure. Okay, so this is what our verification queries are going to look like. Okay. Okay, and what will this verification query do? So this verification query will search for some evaluation of n with 5 time steps in which all the input values are in this range, such that the output value at some time step is at least 16, or is greater than equal to 16. Okay, so you're going to find some such network where the precondition holds, the post condition some such values of the inputs, such that the preconditions hold, the post condition holds for the time unit bound of 5 in the network that has been given to you. Okay, some such valuation is okay. If such a valuation exists, then you know that this property, whatever this verification query holds. So this output predicate typically is the negation of the desired property. So therefore you can verify the, okay. So here the desired property could be that the output at all instances should be less than equal to 15. Okay, the negation of that is at least at one instance the output has to be greater than equal to 16, and this has been encoded as the output predicate. Okay, so this is what it is. Okay, so this is the verification query. Okay, now of course, we can get to the actual verification and how it happens and so on, but let's try to at least see whether this verification query is I mean what will the network what will the verifier return for this, or what should the verifier return for this? Okay, so if you think about it, what is this network doing? Let's try to understand what this network is doing. Okay, So so what happens is that, so this network at 21, what it is doing, it is summing the current value which is coming from 11 and the old value which has been stored at 21. Okay, so at 21, it does nothing but it sums these two values, the old value plus the current input. Okay, so this is what it is doing. Okay, so it will sum the current one plus the old value, and then the sum will be stored in the memory unit, and then once again it will add the current one to the one that is stored in the memory unit. So essentially what it is doing is it's accumulating the all the inputs. Okay, and of course applying relu on that whenever it becomes negative. But let's keep the relu part aside. What 21 is doing is essentially accumulating all the inputs. Okay, so the first time half comes there, so it gets half here. Then 1.5 comes, so it becomes 2. Then -1 comes, so then 2 plus -1, it becomes 1. And then -3 comes, so it actually becomes -2. But then since relu is there, it becomes 0. But at 21, what you're doing is you're accumulating all the inputs. Okay. So if you think about it, what this and yeah, so and not just that it is accumulating all the inputs at till any point, yeah, so till any time step it is accumulating all the inputs. So at every time step it's accumulating all the inputs that it has seen so far. Okay, so in that sense, what 31 gets, 31 has to be bounded by this sum. Okay, the sum of all the inputs. Okay, so at 31 the value can never become bigger than the sum of all the inputs, because it is either the sum of all the inputs or a value which is lesser than that, because whenever it is yeah, I'm sorry, I correct, yeah, I'm sorry, this is not true. Yeah, uh yeah, so 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 first of all, am I audible? Am I making sense so far? Is there somebody who could unmute and say yes, no, whatever?
Yeah.
Correct. Yeah. So what I was saying is that, okay, so you have this pre condition, you have the post condition, you have the network, and you have this bound on the time step. Okay, and you're trying to verify this property. Okay, and after that, what I said might be wrong here, but let's try to see whether this property holds for this network or not. And the claim is that this property holds because what you're doing here, what you're doing for this network is what is at 31 you're accumulating all the values of this input, except that yeah, so if you accumulate all the values, see the values are bounded by 3. Okay, so the values can at most be 3. Okay, so if you accumulate all the values, then it will become 3 plus 3 plus, I mean, if you got the maximum value at every input, then you would get 3 plus 3 plus 3 plus 3 plus 3, which is 15 in 5 time steps. So therefore it can never become 16. That's the rough argument. You can convince yourself that this is correct. Okay, but the rough argument is that, look, it can never become greater than or equal to 16 at any time unit, because even if it is the maximum at every time unit here, it will still be only 15. Okay, if it is less than that, then it will be even lesser. We are not worried about that. But even if it is the maximum, which is, it has to lie between -3 and 3. So even if it is the maximum, it will be 3 every time, and that will give you 15 at max. It will not give you anything more than that. So 16 certainly is out of question, and therefore this query is answered. Okay, so this is the point of this verification. So we'll try to see if this can be derived automatically, that this property holds for this RNN. Okay.
Yeah, another way to look at this, Madhukar,
Yeah.
I thought, is actually what what is intended to be proven is at the end of 5 time steps, your output still remains within that bound. Okay. I mean, and that you're proving by establishing that in each time step, it is less than or equal to 15. Maybe the, since the, what you have as Q is the negation of the property that you intend to prove, which you really, I guess, what you're trying to, the goal of to verify is that, the output should be less than or equal to 15 and less than or equal to 15. And you're establishing that by actually proving that in each iteration, it is less than or equal to 15. So, I mean, I'm wondering if what is the, since you mentioned that Q is intended to be the negation of the property. So what you really are trying to prove is that for every time step, your that accumulated value is less than or equal to 15, correct?
Correct. Yeah, indeed.
Yeah. And if you indeed at any time is greater than 16, I mean greater than or equal to 16, then it is wrong. Therefore, you're establishing that it is less than or equal to 15. Yeah. Okay. Since that is the negation, so that's what I just wanted to add.
Yeah. Okay. Yeah. So this is just an example. So we saw an example of an RNN. We saw an example of a property, and we also saw that the property was safe on that RNN because of that because of the way the RNN was. Okay. So this is something that we have seen in terms of examples, and let's go ahead now. So of course, as I was saying earlier, the idea is to reduce this RNN verification problem into a feed-forward neural network verification problem. And one of the easiest ways to do it is to unroll, which is not what these guys are proposing here in this paper, because unrolling it can be expensive. Okay. Yeah, but if you could unroll, then this is how this is how it look like. Okay, so you could unroll it up to five time steps like this. You will have these 5 inputs, and these 5 unrollings for these could so you will have the memory units can also be be made a part of the whole thing. So here you have remember that earlier you had 4 time steps, and therefore you needed to use the memory unit 3 times. Similarly here, there could be one actual value, and then that will become the memory unit, and then the new value, and then that will become the memory unit, and so on. So you have these 5 values, and 4 of them are memory units when you are at the 5th one. So you can go on doing this. You can keep unrolling, and this becomes your feed forward neural network, and then you can verify this network in using the standard techniques. But that's not what is being proposed here. Okay, so what is being proposed is something else, and this is about circumventing the unrolling. Okay. Okay. So what is it that they're proposing? So you have this verification query, which is a 4 tuple now, right? So you have this precondition, you have the network, you have the post condition, and you have this T max, which is the maximum time bound for which the property should hold. Okay. So you have this 4 tuple, and the idea is to reduce it into a feed forward neural network verification problem, which we know was a 3 tuple, right? So somehow the T factor has to go away. Okay, so what they propose is that this 4 tuple gets changed into this 3 tuple. So you have this verification query phi, which changes into phi hat, and your somehow you take your p and make a p hat out of it. You take your n and make an n hat out of it, and similarly for the q, you make a q hat out of it, and you use the time somehow in this process such that you capture this thing. Of course, when you're trying to capture it's not that phi hat will be equivalent to phi. it'll over approximate it, like how we had seen earlier in the introduction. They had said that they will over approximate the network and then they'll try to verify. So of course, when you over approximate the network and you get this thing as unsat, so when you see that the property holds, then it is fine. But if you see that the property does not hold, then this does not really mean that the property does not hold for the network, the original network also. Okay, so there is this case of it calls for a refinement and so on, which we are going to not look at right now. Okay, so what is the takeaway? The takeaway is that you have your verification query which you have your RNN verification query which you want to transform to your feed forward verification query. Okay, so how do you do that? You do that by doing the following changes. Okay, so I'm looking at these four enumerated points here. Okay, so these are the changes that we'll make. So what is the change to the network? Okay, so the network is changed by adding one additional input neuron to which is called T to represent the time. Okay, and we'll treat it as a real number. Okay, so the network, you add a special input neuron T to represent time. Okay, what else do you do? So for every memory unit, what you do is you replace this. Remember that there was this square memory unit box which was there in the figure that we had seen. So they are suggesting that you replace this square box by a regular neuron, okay, which they call VM to denote the memory neuron. Okay, so you replace this memory unit by a memory neuron and place that memory neuron in the input layer. Okay. Okay, so you place it in the input layer, but then connect it to the neuron that it was connected to anyway. Okay, remember that in feed forward neural networks, you don't have connections that jump a layer. Okay, so this is an exception to that. These connections will jump layers. Okay, so from input, so these nodes will be at the input layer, but they will be connected to their corresponding neurons wherever they are in the system. Okay, so these will be edges which will jump layers. So from the input layer, they can be connected to the neurons in any layer. Okay, and this exception is only for these memory neurons. This exception is not there elsewhere. Okay. Okay, so there are two things that we are doing. We are adding a neuron to represent the time, and then we are putting for every memory for every memory unit, we are putting a regular neuron to represent that. And of course, the edges intact the way they were with the original weight, whatever was the original weight. Okay, so this is how the network is changed. Okay, you must also change the P to P hat and Q to Q hat. Okay, so let's talk about the Q first. So Q does not change at all. So your Q hat is same as Q. Okay, so your network changes in these two ways, 1 and 2. Okay, your Q hat does not change. So your Q hat remains the Q. Okay, so now let's focus on P hat. Okay, so P hat has three components now. Okay, so it should have the original P, which is there, the original precondition of the RNN verification query. Okay, and then there are two more components. Okay, one is a component that constrains the time. So if you want to get an intuitive picture of what is happening, see, you had these input neurons in the input layer, the original input neurons, and you had some precondition on them, right? I mean, precondition typically is constrains the input neurons, right? So you had this precondition on the input neurons, but now you have added more neurons in the input layer. One is that you have added this T neuron, okay, and there are other memory neurons that you have added. Okay, so therefore this P hat, which is the improved precondition, or which is the transformed precondition, must constrain all these things that you have added. Okay, so your P continues to constrain the original input neurons. The second constraint constrains the T neuron, the one that you added in the first point. Okay, So this constrains the T neuron. And then there is this formula I which bounds the value of the memory neurons. Okay, what this formula I is, and what it looks like, and so on, which we'll see later. But I'm just trying to explain what these three parts mean. Okay, so the first part is the constraint that you had originally on the original input neurons. The second part is the constraint on the T neuron, and the third part is a constraint on the memory neurons that you have added. Okay, as step two. Okay, so this is a constraint on the memory neurons. The output, of course, does not change. Okay, yeah. So correct. Okay. So what is the idea? So what is the idea behind this construction? See, the idea behind this construction. So if you remember, what was the query? What was the verification query that we had? So we had this verification query that if the input always lies in the range -3 to 3, can the output ever become greater than or equal to 16? That was the verification query in 5 time units, right? That was the verification query. Now, by transforming, what they want to do is that, so consider that this is indeed possible, that the output becomes greater than or equal to 16 at some tth time unit. Okay, so then they want this new network to be able to capture this property that at tth time unit, for some values of some preceding inputs and so on, or whatever could be there in the memory, for some possible values of whatever you may want to have in memory, and a t which lies between 1 and t max, whatever is the time unit at which the violation is indeed possible. So this change, this transformation allows you to capture the violation if there was a violation possible. Okay, this is what this transformation is making this network capable of. This transformation is making this network capable of capturing the violation if there was a possible violation. Okay, because if there was a possible violation, it will happen sometime between 1 and t max, because that is the property. So therefore it constrains t to be between 1 and t max, so that it chooses the t appropriately, okay, to be the time unit for which it believes that there's a violation. And then the other memory neurons will also be chosen appropriately. Their values will be they are all input neurons now, so their values will be chosen appropriately, such that if you start in a state where you start in some memory state, then for that time unit you'll actually violate the property. Okay, so this entire transformation is just to enable the network to capture the violation if there was a violation possible. Okay, so in fact, it is for this reason why they call this a snapshot query and a snapshot network. Okay, okay, and they say that the intuition behind this construction is that this snapshot query encodes a snapshot, which is nothing but an assignment of t, in which all constraints are satisfied. And of course, at VM represents the values stored in the memory units and so on, so that you can actually have the counter example that was possible there. Okay, so yeah, without getting into the verbosity
But
of the write-up.
yeah, I would also, it can be described in a slightly different way. Okay.
Yeah.
If you are looking at what exactly is happening here in recurrent neural network, it is like it's a loop. Okay, so you are just iterating over a loop, in this case 5 times. Okay, and each time you are and the t is, if you were to be implementing it as a loop, and you are computing whatever the feed-forward neural network is computing, and you're accumulating the value inside an accumulator, which is the memory unit. Okay, so, and the t represents the iteration. So what you're trying to do is trying to make a constraint that the accumulator will have to satisfy in each iteration such that your condition that you want is preserved. Okay, that's another way to look at it. I mean, I think that connection, I'm sure they will eventually establish. So therefore, the T that you're doing represents the iteration, and for every iteration you are hypothesizing that the value in the accumulator, which is the memory unit, is bounded by a certain expression, in this case 3t or something. That is what the invariant, the I condition establishes. Okay, and that is good enough for you. So if you argue that in every iteration that holds good, so you're hypothesizing a condition on that memory unit such that for every iteration that condition is preserved. Okay, so that's the way I look at it. Okay, and that is why the connection with invariants, etc., that you will establish later on holds good. Yeah. Okay.
Yeah, certainly. Okay. So So in any case, so we know the transformation that has been made, right? So this is how the transformation looks like. I'll just correct. So this is how the transformation looks like. So if you see there is this figure on the right of the screen, which has this. Remember this earlier thing with the memory unit. Okay, so now this memory unit, the square box, has been transformed into an input neuron, which is VM21, which is in the input layer. Of course, it continues to have an edge to the neuron with the same weight that was there. And of course, it's only incidental that this does not cross a layer. These edges are allowed to jump layers. This one, since there are not too many layers, this one is looking all nice. But if there were multiple layers, this there could have been a VM4,1, which could have gone to the fourth hidden layer very well. Okay. Yeah. So anyway, so what we have is this input neuron, the hidden neuron, the output neuron, and then there are these two additional neurons that we have. There's a T neuron, which is for the time step, and there's this VM21, which is the memory neuron, which replaces the tilde memory unit. Okay, and yeah. So remember that P was the so the precondition for the RNN verification was that the input at all time units lies between -3 and 3, and the post condition was that the output at some time unit is greater than or equal to 16. Okay, so of course so you have built this snapshot network n hat, which is shown here. You of course replace the memory unit 21 tilde with the regular neuron 21M. Okay, and you connected it to the same hidden neuron with the same weight. Okay, and then there's an added extra neuron for to represent time. Okay. Now, Q, of course, will continue to be the same as the Q. The Q does not change. The post condition does not change. Okay. So now it's only about the precondition. Okay. So the precondition, as we saw earlier, it had three parts. One part is the actual precondition, which is that So now I'm looking at this big formula. Okay. The biggest part of it is the P. Okay, is the P hat. Okay, so P hat has three components. As you can see, there are these three conjuncts in this expression. The first conjunct is the actual precondition that the input always lies between -3 and 3. Okay, and the second part is a constraint on the time that T lies between 1 to 5. Okay, and the third one is an invariant on the memory neuron that has been added, the regular neuron, which is to represent the memory part that has been added here. So this one is a constraint on that one. Okay, so this VM21 is less than or equal to 3 times t minus 1. Okay. How this has been derived is a different thing, and we'll come to this question of how this expression was obtained, how this formula was obtained. So we'll come to this question, but this is just to give you an example of how this may look like. Okay. So this is how it may look like. Okay. So you have your original precondition, you have some constraints on the time, and you have some constraints on the memory neurons that you have added. Okay. And then there is of course this network and the post condition. Okay. And now this becomes like a feed forward neural network verification problem. You can use for instance a reluplex to solve this, or Z3 to solve this. Okay. So this is what we have done. So we had an RNN verification query. We have transformed this into a feed forward neural network verification query. Okay. Okay. So all of this is clear except this part, this formula, the third conjunct in P, which is not clear how this came. Okay. So this part is not clear how this formula came. Okay. Now, of course, you can see that in the presence of this formula, the precondition and the network does imply the post condition. So basically, correct. No, it does not imply the post condition. Yeah. So what I meant is that if you start in a network where the precondition holds, and if you start where the pre in a state where the precondition holds, and if you follow the network, then you will not reach a state where Q holds. Okay. This query is unsatisfiable. It is not possible, and therefore the verification query is so basically your property holds. The property, remember, was a negation of the. Okay. So this is the main result of this paper. Okay. So the main result of the paper is just this, that if you have a verification query, if you have an RNN verification query which looks like this 4 tuple, okay, then the corresponding FFNN verification query, which is this 3 tuple, okay, and can be written like this, and the point is that this is, if you transform it like this, then it is always an over approximation, which is to say that if the property holds in the feed forward network, then the property certainly holds in the recurrent neural network. If the property does not hold, then you cannot say anything about whether it holds in the RNN or not. Okay. So this is the main result of this paper. Okay. So far, I'll just quickly reiterate what I have said so far. So you have what are called these recurrent neural networks. These recurrent neural networks are important because they allow you to deal with streaming inputs or inputs of variable lengths. Okay, these are not very different from feed forward networks because you can unroll them, but unrolling is not an interesting thing to do because it complicates your verification exercise. Okay. So for verification exercise, what you can do is you can transform the RNN verification query into a feed forward neural network verification query. And this is what the transformation looks like. And then you can argue that, these transformations are an over approximation. Therefore, whenever the property holds in the transformed network, then it holds in the original network also. Okay. So this is the summary of the story so far. Okay. And all the parts are clear except this invariant part here, which somehow was magically written here. We don't know how it came. We don't know whether it is correct. We don't know anything about this. Okay. The rest of it is clear. Okay.
Yeah, but I definitely, one should add this thing. Okay, so he has applied it to, this is a comment. So this, for people that are familiar with verifying loops, okay, using loop invariance, this is nothing very profound. Okay, so so some of you might be familiar with that, not everyone. So the way, if you encounter loop in a program, and the way that you verify is, of course, you can unroll the loop forever, and if you know how many times that thing is. Another way to do is to what is called cutting the loop. You cut the loop and you just propose what is called, traditionally called loop invariant. Some of you might be familiar with that, and some of you may not. And and if you propose that, hypothesize some invariant condition. It is invariant in the sense it holds good every time that you iterate through the loop. Then you can just verify that that condition that you hypothesized is preserved by the body of the loop. Okay. And and that's what establishes that as an invariant. Then you don't need to unroll the loop. So you prove that the invariant is preserved, every time around the loop. Now, the contribution that he's using that concept of the loop invariant, and Madhukar will get to that later on, in what sense it is an invariant. And I think the one novel aspect that he does is he applies that and shows how that establishing that it is an inductive invariant and showing it, cutting that loop that you would normally do, can be done in the context of a neural network, okay, by introducing these new nodes and then reducing into feed forward. And I think that's how I look at this this paper as a main contribution. But the basis of loop invariance and what is an inductive invariant, those things are all have been developed as part of program verification. Okay, and that is not his original contribution here. Those are very well known concepts, the concepts of inductive invariant and how you cut the loop and then don't need to unroll the loop. You can verify the total effect of the loop by proving something just for one iteration of the loop. Okay. So that is my 2 cents worth of how I look at this thing. Okay. Yeah. And that may, some of you who know about loop invariance may appreciate and may wish to compare this, what is going on here with it. Okay.
Yeah. Yeah. So in the remaining time, so there are two. Yeah. So if we see what are the two things that are not clear as of now. So yeah. So one is that how do we obtain this, and as sir was saying, so this comes from invariants or loop invariants and inductive invariants and so on, and which is not, there has been a lot of work on how to obtain inductive invariants and loop invariants and so on. So this is, so we'll get to this part later in the next class. So that's just one of the problems. The other problem is that whether it is correct, given such a formula, is it even correct to have this? Okay. And this is something that we'll see in the next.
Whether it is inductive or not. Okay, that is checking whether what you've proposed is indeed inductive. It's an inductive invariant, right? That's what you have to check.
Correct. Yeah. So so they say that the key assumption in the reduction was that this I was available, right? So this entire reduction follows because you had this invariant I, which bounds the values of these memory neurons as a function of the time t, right? So this invariant, which was, in this case it was 3 times t minus 1 or whatever. So this was made available to you. Okay, and suppose there's a system which can give you these candidate invariants. How, I don't know. Maybe we can we'll get into the details later. But suppose somebody can give you, at least can you check whether these are correct invariants or not, is the point. Okay, and we'll just see very quickly how to check that these are correct. Okay, and we will take the same example too. to see that these are, yeah. Okay. Yeah, sorry about this. Yeah. Okay. Yeah.
It's a good time to ask if people have any questions.
Oh, yeah, certainly. Yeah. So if any of you have any questions,
Yeah, the remaining two parts, like what Madhukar said, was checking if indeed what you're proposed is an inductive is inductive as in that condition I. And the third thing is how do you even generate such invariants? Here it was manually generated. Before, Madhukar, I don't know what your plan. You plan to cover those two things or some
correct. So
part?
I'll cover this one part. How to check is
Yeah.
one part, and how to obtain is one part. So obtaining is what I'll deal with in the next class. Checking is what I'll do now.
Okay. Yeah. So at that point, before he gets to the checking if what you propose, either manually or generated, is an inductive invariant, in terms of, for that feed-forward network. Any questions?
So in the resulting network, we had an input node for the time. What was that input node connected to?
Yeah, like I said, the way I view it is iteration. Okay, iteration number. I mean, if you know for every iteration you have to show that condition. If you assume something that in every iteration that I that you proposed must hold good, that is one way that I look at it. T actually corresponds to the loop counter. Okay.
Right, but in this case, is the loop counted even like what is it connected to within the neural network?
So it's
Like,
not connected to anything. It's just there so that you can take it as an input.
As an input.
Okay. So, right, okay.
Because
So
the
essentially
invariant is going to be in terms of T. So you should,
and that is the only place where we're using T.
Yeah,
that is
it
the
is.
only place where we use.
Yeah, it is not manipulated. That's a good observation. It's not manipulated by the network. Okay, so it's some arbitrary input that is constrained symbolically to be between 1 and the max iteration. Okay, so and you'll have to establish that indeed the invariant is true for every iteration between those two limits.
So since it's not manipulated, we could hope to find an invariant that is independent of T, right? I mean, maybe.
See, the invariant is invariant with respect to T, but then the value, the constraint may be dependent on T. Okay, in this case, it's actually dependent on T. If you observe, the constraint, the bound on the memory component is 3 times T.
All right, yeah.
You see, so the invariant, usually is dependent, among other things, the loop counter as well with the T here. Okay, it may be dependent on other values or inputs and so on, but in this case, it happens to be T. So that's the critical thing. So the invariant condition itself can be dependent on T. That's typically how it is in all loop invariants, okay? So usually it is dependent on the iteration number, the iteration of the loop. It could be, or sometimes it may not be, okay? There are also cases where it is not, but in general it could be. That's why T has to be preserved.
And if you find something which does not involve T, but if it is still good enough to prove the property, then that's good enough.
Yeah, it's good enough, but the way that he is doing, I mean, because his property is such that it has to be preserved every time, okay, in the loop. I mean, that's the way he has expressed it. But yeah, you're right, Madhukar, that if indeed you can express an invariant that is independent of T, that's good enough too.
Correct. Yeah.
But in some cases, you will have to involve the iteration.
Correct. Yeah. And also to answer your earlier question, see, there is this thing that they have said, and I'll just point you to this section of the paper. So this is called time agnostic properties. Okay. So they say that in the construction, in the aforementioned construction of phi, the original properties P and Q appear either fully or as a conjunct in the new this thing. It is not immediately clear that. So basically, what they are saying is that this internal things could also have a time. So you could talk about the input at the seventh time. Okay, and that could be a part of the precondition. Okay, so what they are saying is that for simplicity they have assumed that P and Q are time agnostic. Okay, that is, they are given in the form that that P will be a conjunct for all time units and Q will be a disjunct for all time units, where psi1 and psi2 contain linear constants over the inputs and outputs of n respectively at time t. Okay, so and of course later they say that, look, they say that this assumption can be relaxed significantly, but I have not read this part. Okay, so what you're saying is that this, yeah, the core parts of the precondition and the postcondition are time agnostic. They need not be so, right? And in that case, it'll, there'll
Yeah,
be, it can become more difficult.
right.
Because
So, so
that depends on whether your what your property is. Okay, so if your property is somehow dependent on the number of times you iterate in the loop, then it is dependent. Okay, if not, then it is not. So consider the factorial program. So in the factorial program, so in the factorial program, it is not because the number of times you iterate is exactly equal to the input, one of the input numbers. Okay, but in some cases, what you compute might be dependent on the number of times that you iterate through the loop. In that case, you may have to have the P and Q also dependent on at least the number of iterations. So if it is
yeah.
not, then you can express it.
Yeah. Okay.
A classic example in this case, okay, where it is not time dependent is in those cases, for example, if you have two variables that maybe you increment both of them by the same amount, okay, X and Y. So one invariant condition could be that X always is equal to Y, okay, initially if X is equal to Y. That doesn't depend upon the iteration at all. At all times, X is equal to Y. And that is because you're incrementing inside the network both X and Y by the same amount, if you happen to be doing that. So there will be some situations where it is not dependent on T. So in which case, you can make P and Q agnostic of T. Otherwise, you have
Right.
Yeah. Yeah. So anyway, so I'll very quickly, complete this point that I was making. That is about verifying. So given a candidate, how can you verify that it is correct? And then we'll see how to find candidates. Okay. Yeah. So this one, yeah. So once again, we'll just take this example that we have, and then we'll try to see how this can be done. Okay. So this verification can be done by induction, and then it can be transformed as a neural network verification query. We'll see how. Okay. So suppose you have been given this invariant that V21M is less than or equal to 3 times T minus 1, which was the expression that we were seeing earlier. Okay. Now the point to understand is that so of course the first thing that is checked is that it holds at every initial state, and this is true in this case because in the initial state the time is equal to 1, and therefore 3 times time minus 1 is 3 times 0, and you have 0 in the memory unit in the beginning anyway. So 0 is less than equal to 3 times 0. So therefore this property holds. Okay. Okay. And now the idea is to assume that this property holds for a given state, and then to argue that, it will hold in the state to which you can go to from there. Okay. Okay. So this is what they say. So they say that, now assume that I holds for this state, and prove that it holds for this state. So a is nothing. A is just the value of all the variables in the network. Okay. A is the current assignment to the nodes in N. Okay. So it says that, if the property holds, at some point, then it also holds in the next time instant. That's what you want.
Any time t that is within those bounds, then it holds good for the next time.
Correct. Okay. And the way this is done is by creating this snapshot, and then by asking this property. Okay. So here is what is done. Okay. So you have this original input property which says that, the input at all time instances will lie between -3 and 3. Okay. Okay, so what this gets transformed into is of course that the input will lie between -3 and 3, and that VM21 is less than equal to 3 times t minus 1. Okay, so this is what your property gets transformed into. Okay, and so what is it that you want to check? Remember that, we are checking this by induction. We are checking whether the property holds by induction or not. So you have assumed that, this property holds till some point, and then you are trying to make a transition and so that this property does not hold. Okay. So in the next time instance, this property does not hold is captured
negation of the property. Negation of the property.
Yeah, the negation of the property. Okay. So this is captured by Q prime, where it says that, look, at time instance t plus 1, this will not be the case. So V21 will not be less than equal to 3 times t plus 1 minus 1. Correct? So t becomes t plus 1. Then this is the same expression, and you negate the property. Okay. So you say that, look, I want to find out if it is possible for me to reach a state, basically, if it is possible for me to be in a state where the property holds, and then after one time instance from there, the property does not hold. Is it possible that this can happen? Okay. So what you do is you encode this, that from the state P prime, can you go to the state Q prime by following a snapshot of this network? And this you encode as a feed forward neural network query. Okay. And then if this is unsat, then what you have is indeed an invariant. So basically, you can never go from a state where the property holds to a state where the property does not hold. This is the definition of being an invariant. Okay. This is something that will always hold. Okay. So you check two things. You check that this is true in the beginning. Sorry. So in the last page, you check that it is true in the beginning. And now you are checking that if it is true at some point, will it also hold in the next time instance? Okay. So checking whether it is true in the beginning or not is trivial. You can check it. To check whether it is to check whether it is inductive or not requires you to make one neural network verification query, one FNN verification query. So this can again be done by the Reluplex engine or C3 if this is simple enough. But that's the idea. So,
if you want to compare it to program verification with loop, for those that have seen, this is like the body.
Yeah. So in the
body. Okay. The body of the loop is your feed forward neural network. Okay, with a few additions to inputs and so on.
Correct. Yeah. So what I'll do is in the next class, I will compare this to what is. So I'll start with what are invariants for in program verification and what are loop invariants, and then I'll reiterate how this verification makes sense, and then we'll go to how these can be inferred, which is the next section. Okay. So in the next one, in the next class, I'll start with loop invariants. Then we'll reiterate why this kind of checking makes sense, and then we will see how these invariants can be inferred. Would that be okay, sir?
Yeah, I think that's the plan. That's the perfect plan. One thing that I wouldn't mind people actually, I mean, if I, whether we can do, some background on if anybody who has more experience with neural network, the can't the can't the kind of application scenarios for RNN, okay, to have where they are used in what way. I mean, I think you gave a good intuition as to where they might be, okay? So whenever there is some streaming application and so on. But to really understand what are the kinds of invariants that are really needed, what are the kinds of properties, you need to have a good understanding of where RNN, the looping aspect can be exploited in practice. Okay, so I don't know if we can have some discussion about that. If people want to, or anybody that independently.
Yeah, so yeah, certainly. Yeah. So if anybody has any experience or any ideas, then they can, and I'll also try to find out what.
And then even in the task that you are implementing as part of your project, if it makes, it would be just, I mean, I'm not making that as a requirement for you for the project, just to think if indeed it even makes sense for you to apply the RNN concept in your case, because some of you are doing, I guess, I don't know if anybody is working on some language translation. There's some talk of language translation. Some people are working on this, in a picture in motion and those kinds of things. Or even, where Sahil and Zubin are working on some things that requires backtracking and so on. So if indeed, if you saved some information from the previous application of a neural network, the same neural network, if it can be used in the following iteration, makes sense in the context of your project. If you can think, maybe it doesn't make sense at all in that case now. It does make sense, so now it's worth just exploring and thinking that. And if you have any feedback and thoughts to add, I'd be more than happy to listen as part of the discussion after Madhukar covers his portions. There's one suggestion I have.
So I'll upload this paper after today's class, which is right now, and then in the next one, I'll whatever slides I was trying to prepare and including some for loop invariants, I'll try to upload them after.
That will be good if you could upload the paper.
Yeah, certainly, I'll do that.
Okay. Anything? Any other questions you guys have? If not, thank you, and I will stop the recording.